All right, time to start. They didn't leave any full batteries, so my voice might cut out at some point. If so, tell me, so I can change the battery. I've got a bunch of batteries that all have 10% left, and they'll have to do. I'm going to continue one last little bit about PCA, last Monday's topic, principal components analysis. We covered the general ideas, and I want to point out an alternative way of computing the vectors and eigenvalues that are associated with PCA. So what I said last time is that we take an eigendecomposition of X transpose X, where X is our design matrix of sample points. And the problem with even just computing that matrix, X transpose X, before you do any eigendecomposition, that already takes n times d squared time. If d is small, this is no big deal at all, just do it. But if d is big, then this is actually getting expensive, and it's actually faster to do something else. There's another potential problem as well, which is that when you take the eigendecomposition of X transpose X, you're making your system a little bit more poorly conditioned than it needs to be. Meaning you've kind of squared X, and in doing so, you've squared the singular values of the matrix, which tends to make it harder for the numerical algorithms that do an eigendecomposition to give you really accurate results. So the singular value decomposition solves both these problems. Some of you have already seen the singular value decomposition in other classes. I think, is it 16b or 16a? B, thanks. All right, so if you haven't, I'm going to give you the short version today. I don't have time to go into depth on the SVD, but if you haven't heard of it before, I'll tell you what it is shortly. And the main point is that instead of doing an eigendecomposition of X transpose X, we're going to compute a singular value decomposition of just X, and we're going to get the same vectors and indirectly the same values. Now, I really like the singular value decomposition. It's kind of like the eigendecomposition, only better. The eigendecomposition, well, first of all, it only applies to square matrices, and then it's only nice for symmetric square matrices. Non-symmetric matrices, their eigendecompositions can be really crazy. Jordan canonical form and stuff like that. Singular value decompositions. Every matrix has a singular value decomposition, whether it is square or not, symmetric or not, and it's pretty easy to understand in all cases. All right, so what is this singular value decomposition of X? Well, I take my matrix X and I write it as a product of three different matrices, U, D, and V transpose. If the number of sample points is greater than or equal to the number of features per sample point, which is usually the case for most things that we would apply the PCA to, then you can imagine it appearing in the following form. So first, let's look at our design matrix X. So I'm saying, when I say n is greater than d, I'm saying that X is taller than it is wide. This is an n by d matrix. And we're going to write that as a product of three other matrices. So the first one, I'm going to make it the same shape as X, that's U. There are several variations on that shape, but before we get there, let's look at the other two matrices. Then there's D, which is going to be capital D, is going to be a little d by little d matrix. Again, D is the number of features. And then finally, we have V transpose, which will also be d by d. Now, the matrix D in the middle is special. It's always a diagonal matrix. So I'm going to name the elements on its diagonal delta 1, delta 2, and so on up to delta D, and everything else is a 0. So that's a diagonal matrix. The other matrices, U and V, have the nice property that they are orthonormal, meaning U transpose U is the identity matrix. And likewise, V transpose V is the identity matrix. And so when you see that, that means two things. The off-diagonals of the identity matrix are telling you that any two columns of U are orthogonal to each other. And the ones on the diagonal of the identity matrix are telling you that the length of each column of U is 1. So again, I'm talking about the columns of U. I'm going to give them sort of a non-traditional name here. This is breaking my usual conventions. But the first column of U, I'm going to call it U1 with a little u. The last column of U, I'm going to call it UD with a little u. And U transpose U equals I is a short way of saying that all these columns are orthonormal. Again, they all have unit length and they're orthogonal to each other. And these columns are called the left singular values of x. Sorry, left singular vectors, pardon me. And V is basically the same, although this is V transpose, so the columns of V are horizontal in this figure. So we're going to call the columns of V, V1 through VD. And those are also and those ones are called the right singular vectors of x. And the diagonal entries of the matrix in the middle, the matrix capital D, remember they are delta 1 through delta D. Are called the singular values of x. And those are always going to be non-negative by convention. And that they're non-negative by convention, this is what I mean. Suppose that one of the singular values was a negative number. Suppose that delta 1 was negative. Then what we could do is we could replace delta 1 by minus delta 1, and we could replace V1 by minus V1, and then we would have another decomposition that is also equal to x. But now we would have a positive value for the singular value instead of a negative value. And since we can do that, we always do. We just say, by convention, the singular values will never be negative. We'll just make them positive. Now, one thing I want to point out about this matrix decomposition is that since D is diagonal, you can write it in a form that is a little simpler than full-fledged matrix multiplication. You can really think of it as just the sum of D outer product, vector. So we're going to have D matrices, each one of the form delta I times ui times vi transpose. Again, that's not an inner product, ui times vi, that's an outer product, so it's going to give you a matrix, an n by D matrix. And each one of these matrices is rank 1, because an outer product of two vectors always has either rank 1 or rank 0. It could be rank 0, I should say. It's not always rank 1. It could just be 0. And then when you take the sum of those D rank 1 or rank 1 0 matrices, you get a matrix X, which could have rank up to D. Some of the singular values can be 0. They can't be negative by convention, but they can be 0. The number of singular values is equal to the rank of the matrix X. So for instance, let's suppose X is a centered design matrix for a bunch of points that all lie on a line. Then X is going to have rank 1, because all the points lie on a 1. That's a one-dimensional subspace. You're going to get just one singular value that's non-zero. And if your centered data matrix lies on a subspace of dimension R, then you get R non-zero singular values. So one other thing I want to mention is that there are several different takes on the singular value decomposition that depend on how big or small you want to make these matrices U, D, and V. This is the one that's best suited for our purposes usually. However, if you have a situation where the design matrix X is actually wider than it is tall, if this were really wide here, then what we would do is we would make U be the square matrix. So U would be square, and I'm sorry, let's imagine it's this size, like turn X sideways. All right, then U would be square, and D would be the same size, and V would be wider than it is tall. So that's what you do if X is wider than it is tall for our purposes. Any questions about that so far? All right, there's a very important relationship between singular value decompositions and eigendecompositions, which is what allows us to use the SVD for principal components analysis. So these right singular vectors that I've just given you of X, they are also eigenvectors of X transpose X. So by finding the right singular vectors of X, I have found the eigenvectors of X transpose X. They're the same thing. What are the eigenvalues associated with that? They are the squares of the singular values. So if Vi is a right singular vector of X with value delta I, then it's also an eigenvector of X transpose X with eigenvalue delta I squared. This is actually really easy to show. Let's just take X transpose X and write out each X in terms of the singular value decomposition. Well, X transpose is going to be VD U transpose, and X is going to be UD V transpose. And when you do that, you'll notice that, well, U transpose U here in the middle, remember I. So that just goes away. That part disappears. And what you're left with is VD squared V transpose. And if you remember what an eigendecomposition looks like, that's the form of an eigendecomposition. You have an orthonormal matrix V, and you have a diagonal matrix in the middle. That's an eigendecomposition. So that's why that is true, that fact. So going back up to this illustration here, what that means is that these vectors V, these are actually the principal components. The vectors that we need to do PCA. And the SVD also tells us the eigenvalues. What we have to do is we take these singular values and we just square them all, and that tells us the eigenvalues associated with those eigenvectors, those principal components. So what makes the SVD useful? One of the things useful is that if D is large, you can often compute the SVD faster than you can even compute the matrix X transpose X. So what is the running time for finding, well, let's look at a special situation. Remember, we don't usually want all of the principal components. We just need some of them, the ones associated with the biggest eigenvalues, or in the case of the SVD, the ones associated with the biggest singular values. Well, so suppose we just want the k greatest singular values. And the corresponding right singular vectors. Well, there are solid algorithms that do that in big O of n d k time. And remember, I told you it's n d squared time just to compute X transpose X. Well, if k is a lot less than d, this is a lot faster than just even computing X transpose X. So that's pretty great. Yeah? Oh, usually they are, yeah. It's not really important for my presentation right now, but yes, the convention is to, I think, typically put the biggest one in the upper left-hand corner, which of course is the opposite of the convention I used for eigenvalues in the last lecture. Different people use different indices. You're saying, is the order NDK time related to the? That's to calculate part of the SVD, yeah. So we are only computing the left singular vectors and right singular vectors in the first k singular values. That can be done in NDK time. In fact, if you're willing to do an approximate SVD, one that's maybe not exact but pretty close, there are approximate randomized algorithms that are even faster and can produce an approximate SVD in order ND log K time. And I've included a link to one of those projects in the lecture notes if you're curious. So there's one more really important connection between the SVD and the principal components analysis that you need to know if you're going to implement it using the SVD, which is that you get the principal coordinates more or less for free. Because once you've computed UDV transpose, then just by looking at UD, looking at the rows of UD, that gives you the principal coordinates in the k-dimensional space. So specifically, when you have an input sample point xi, remember that when you project that down to k-dimensional space, you're giving it k principal coordinates, which are of the form sample point xi dot product with principal component vj. And so that dot product, I'll remind you, is called a principal coordinate and is essentially our way of plotting the lower dimensional space. Well, that is equal to delta j times entry with row I and column j of the matrix U. So what I'm telling you is that once you've run PCA, you don't have to do an additional step to project all the points down to the lower dimension. It's already been done for you by PCA. It's coded right there in the other two matrices. So you don't need to explicitly compute these dot products. They're essentially already done for you. Any questions about that? All right, now we were changing topic. The rest of today's lecture will be about clustering, which is a different kind of unsupervised learning. Completely different from PCA. So the idea is someone gives you a bunch of sample points and you want to partition them into clusters. And roughly speaking, the points in a cluster ought to be more similar to each other than they are similar across clusters. Oops. So the first thing you might wonder is, why would you want to do this? There are a lot of applications for this. One is discovery. Suppose that you have a database of songs and you have a list of songs that you like and you want to find other songs that are similar. Then you could organize a big database of songs into small clusters and then look at which clusters include songs you already know you like. Another example is maybe you're selling products and you want to figure out what types of people are buying your products and why, and what kinds of groupings of products they like to buy. And so this allows you to determine different market segments, like people who are young parents might buy very different kinds of items than retired people. There's also forms of hierarchical clusters that are used to discover hierarchies And kind of a classic example here is in biology. If you have the genes of a bunch of different species and you want to see how closely related they are, then you can try to cluster them and do it in a way that is hierarchical, that gives you some clues what animals might have evolved from what other animals, or be closely related. Another application is called quantization, and here the idea is that you want to just compress a data set by reducing the number of choices. Back when color monitors were expensive, this used to be done a lot with colors, for instance. In an image, you find colors that are almost the same and you group them together to reduce the number of bits you need to express the image. Another application is graph partitioning, which is used for image segmentation to be able to figure out what the different parts are of an image. Like, if you have a photo of the front of this room, you want to be able to separate the blackboard from the screen, from the table. So image segment estimate. Or if you have a social network, you might want to figure out which are the groups that are most strongly bonded together within that network. So here's one example of clustering that I found on the web that I just really like. Somebody quantified baseball pitches and specifically did it with a famous player named Barry Zito. And so got a 3D plot here that shows the starting speed of the pitch and two different kinds of spin placed on the ball when the pitch is thrown. And they've clustered these points. And what you find is that there really are notable differences between different kinds of baseball pitches. So you can see that, say, curveball, for instance, which are the light blue, are in a distinct part of space from, say, sliders, which are the dark blue. So I thought this was interesting that you can really quantify different kinds of pitches and how they differ from each other. Now, the most famous clustering algorithm of all has a couple of names. Most commonly, it's called k-means clustering. But it's also known as Lloyd's algorithm, and you'll sometimes see it called that in the literature. And this was invented by Stuart Lloyd, hence the name, in 1957. So in this problem, somebody gives you n points in some space, usually Euclidean space, but not always. And you know how many clusters you want. So you know that you want to partition them into k clusters. And we won't really have time to talk about how to pick a good k, although validation is always the answer to everything. But let's assume we know k. Let's assume we know how many clusters we want. So the goal of our algorithm is to assign each input point, x of I, a cluster label. Now, this is an unsupervised learning algorithm, so we're not given any labels as input, but we can make up labels internally and use those as cluster numbers. I'll use the letter y for whatever cluster label we've assigned internally, and that has to be in k. As the name k-means clustering suggests, we care a lot about the mean of each cluster. So cluster I, its mean, we're going to write it with the notation mu subscript I, and that's going to be 1 divided by the number of sample points that we have assigned to cluster I, times just the sum of the positions of all of the points in cluster I. Again, just a reminder of what Ni is. It's the number of points in cluster I. So with those definitions, I now specify this as a formal optimization problem. We want to find a vector of assignments y that minimizes the sum of the squares of the distances from points to their cluster centers. All right, so let's look at what this means. The first summation is summing over all the clusters. There are k clusters, so I is an index over all the clusters. The second summation is taking all of these sample points with index j that we have assigned to cluster I. And for each sample point, we're subtracting it from the mean of its cluster, the cluster we've assigned it to, and take the square of that. All right, so we would love to optimize this problem exactly, but the bad news is that this is not a purely numerical problem. Remember, y is cluster numbers. It's a discrete optimization problem, and it's an NP-hard discrete optimization problem. If you don't know what NP-hard means, take CS 170, but the short version is it's really, really hard. That doesn't mean you can't solve it. There is a very simple algorithm that solves it in exponential time. You can solve this problem. You can find the optimal assignment in big O of n times k to the power of n time. And the way you do that is you just try every possible partition. There's only a finite number of partitions of n points into k clusters. Try them all, score each one, pick the one with the lowest score. So if n is large, you don't have enough time, unfortunately. If n is small, you could actually do this. If n is 10, you can do this. But if n is 1,000,000, you can't do this. So use heuristics. And again, the most famous heuristic is k-means. So the idea here is we're going to alternate between solving two different simpler, easier optimization problems. All right, optimization problem number 1 is we are going to fix all the yj's, meaning for the moment, I'm not allowed to change the cluster assignments of my sample points. And while I'm holding y fixed, what I'm going to do is I'm going to minimize this expression, but I'm only allowed to change the mu i's. So we can update the mu i's. having done that, now I'm going to solve a second optimization problem where we've swapped the roles of the yj's and the mu-i's. So now what we're going to do is we're going to fix the cluster centers. You're not allowed to change those. But then we are going to minimize this objective function. But now we're only allowed to change the cluster assignments and nothing else. So we update the yj's now. And so you go back and forth. You solve problem 1, you solve problem 2, you solve problem 1, you solve problem 2, over and over again. But eventually you need to stop. So when do we stop? You halt when step 2 doesn't change anything. Because after that, you're not going to make any further progress. Question? Why the problem is NP-hard? I don't really have an explanation why the problem is NP-hard. I mean, there's a proof. It's not an easy proof, I don't think. It would, most NP-hardness proofs, you need half an hour to do them. So I'm just saying, sort of take my word for it. Other questions? All right, so again, we have an assignment of points to clusters. Then we compute the cluster means. Then we reconsider the assignment. A point might change clusters if some other cluster's mean is closer than its own cluster mean. Then you repeat this over and over again. So let's go through this in a little more detail. What does it actually mean to optimize that objective function subject to these constraints? Well, all right, step 1, again, the yj's are fixed, so can't change the cluster assignments. I'm just going to update these numbers, mu of I, minimize that expression. And you can show by pretty straightforward calculus that the correct answer is to compute the mean of each cluster. So my point is that picking the mean of each cluster to be mu I is what minimizes this expression. By the way, this is easy calculus, so I leave it. Step 2. All right, now the mu-i's are fixed. The cluster centers aren't changing, but we can change which cluster we assign each point to. So I think it's kind of obvious that if your goal is to minimize this expression up here, that you should just, for each point, pick the cluster center that's closest to that point. That's how you minimize that when all you can change is the assignments. And so step 2, the optimal vector y of assignments assigns each point xj to the closest center. Mu I. Though I need to make one adjustment here. Sometimes there's a tie. Sometimes there are maybe two cluster centers that are exactly equally far away. If one of the choices is for xj to stay in the same cluster as the previous iteration, then you should always take that choice, because otherwise you might never halt. You could just flip back and forth, one point going back and forth between two cluster centers that are equally far away, and then you never know you're supposed to stop. So you should only change your cluster center if you find another cluster center that's strictly closer. All right, so both of these steps, they change. They, in a sense, optimize our objective function, but not for all the variables at once. Neither step will find both the optimal mu_i and the optimal yj's that work together. Instead, we update one at a time. So will this always find the true minimum? No. It's a heuristic, and sometimes it fails to find the optimal solution, but it usually finds a pretty good solution. So here's an illustration of what the algorithm looks like. In this example here, the numbered steps are reassigning the data points to new clusters, and the even-numbered steps compute the new means. So starting at the upper left here, step 1, we have two means that are sort of pre-specified there and there, blue and red, big blob there, and we classify all of the other points according to which of those two cluster centers is closest. And by the way, this is the bisector, the line that's exactly halfway between the two cluster centers, orthogonal to the line through the cluster centers. And so whichever side of that line you're on, that tells you whether you're going to be assigned to the blue center or the red center. Then step 2, you'll notice that we are computing new means. So we have moved the two means to new locations. The colors of the points haven't changed, though. That happened in 3. Now, notice the means are still in the same location as in step 2, but we've recolored all the points. Then we change the means again in step 4. The means move to these two locations. In step 5, the means do not move, but we recolor all the points, and so on. By this point, we've reached convergence. Any questions about that? Yeah. I'm going to talk about initialization next. That's kind of a topic unto itself, so let me get there when I get. But first, other questions other than how you initialize this? Okay. Well, yeah, it's the obvious question, of course. Yeah. Right. No, let me put it this way. Don't think of mu_i as being, by definition, the mean. Think of it as being, by definition, the thing that optimizes that formula. And then we show that that happens to be the mean. Here's a little animation of k-means clustering with a larger example. So you can sort of see it goes pretty fast, many iterations at once, but we start with 4 cluster centers in these 4 locations, and then we run it. That's a lot of iterations in a short period of time, but you can see that eventually it settles down. I think it's nice to sort of see how that works in a large example. So before I get to initialization, though I'm going to get there soon, let me first point out that both of the steps in our alternating 2-step algorithm, they always decrease the objective function unless they change nothing at all. And that is good news because what it means is that the algorithm will never loop back and return to a previous assignment that you visited in the past. It's always, in a sense, making progress downhill. It can never go back uphill. And because of that, and the fact that there's only a finite number of possible assignments, that means that the algorithm has to terminate. Now, that doesn't mean it has to terminate in polynomial time because there are an exponential number of possible assignments, and you might have to go through a lot of those, but it will terminate if you run it long enough. And in practice, it usually terminates relatively quickly. You can, if you were very clever, devise theoretical examples of point sets where this actually takes an exponential number of iterations, but that never happens in practice. You really have to design a pathological point set to get that to happen. So in practice, it's usually fast. The only catch is that it does not always find the global minimum. It often finds a local minimum, which is not surprising because this is an NP-hard problem. NP-hard problems tend to be hard to solve. Let me just give you a quick example of k-means going wrong in a kind of obvious fashion. So like, take a look at this picture here. When you look at these points, suppose I want to do 4 means on that. So I'm trying to divide those points into 4 clusters. Well, as a human being, you look at it and you see 4 clusters, right? It's kind of obvious how this should be clustered into if you want 4 clusters. Well, suppose that we start with the cluster centers being here, 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 and here, and we run k-means. Will it find those 4 clusters? Here's the next step. You can see that some of the clusters are starting to move out, and that seems like a good thing. Moving out further, but wait, something's wrong. The brown one isn't really moving out far enough. It's kind of moving back to the left again now. This guy here is not going out and exploring the territory as we hoped it would. Instead, you essentially wind up with this as the solution. So what's going on here is that 2 of the things that I, as a human, think should be separate clusters have wound up being 1 cluster. And then this thing, which I think should be 1 cluster, has wound up as 2 clusters. Both those cluster centers just kind of fell into the gravity well there. We have 1 good cluster here, but this kind of looks like a failure. And honestly, it's a hard problem to solve well, reliably all the time. So any questions about that? I'll talk about how to initialize this algorithm next. All right, I told you the algorithm, but I didn't actually tell you how to initialize it yet. And that's because there are several different possibilities. The 2 best known are called the Forgy method and the random partition method. And so the Forgy method, we just start by choosing k random sample points from our input and say, okay, those are the initial cluster centers. So we start off by initializing the mu i's to be random sample points. And then we go to step 2 of our. So run step 2, then run step 1, then run step 2, then run step 1. Random partition, on the other hand, what we do is we start off by initializing yi randomly, the vector y of assignments. So we're going to randomly assign each sample point to a cluster. Making sure that every cluster has at least one point in it. And then we go into our regular loop, but we start it with step 1. So step 1, step 2, step 1, step 2. I'll tell you one other starting method that I find really interesting. Some researchers have an algorithm called k-means plus, which it's standard k-means, but with a special initialization. It is like the Forgy method, so you choose random points to be initial cluster centers, but you don't choose them uniformly at random. Rather, you have a biased distribution for how you choose those starting points. And the main idea here is that you choose the centers sequentially, and each successive point, you choose it with a preference for points that are far away from the other cluster centers that you've already chosen. So you choose your first point uniformly at random. The second one, you prefer points that are far away from the first one over points that are close. It's still random, but it's a biased distribution now. K-means plus plus, although it's a little more work, it works well in theory. There are proofs about it. It works in practice. Regarding the other two, which one is better? Forgy seems to be a little better on average than in random partition. But Wikipedia mentions that there's some variants of the k-means problem for which random partition works better. Any questions about that? Sorry, say that again? No point what?
No points belongs to the brown cluster. It's in the second graph. And that means
there's one point that belongs to the cluster, which is the cluster center itself is a point is a sample point.
So I mean, is it possible for us to initialize 4 clusters, but finally we only get 3 clusters contains the data points?
So I think you will always. So the question is, can you ever get one of the clusters emptying out so that you just have no points in a cluster? And that actually might be possible. Yeah, that might be possible. I think that can happen. One of your textbooks, in talking about the fact that we are initializing k-means with a random method, whether it be Forgy or random partition, they show you, well, what happens if we do this multiple times and each time the random number generator is different? Well, so here what they did is they took this point set, they ran k-means with k equal 3 clusters. They ran it 6 times, each time with a different initial start. In this example, they are using the random partition method to initialize. And what you'll see is that it does not always find the same local minimum. Leaving aside the fact that sometimes the colors get swapped, well, that doesn't really matter. But what you'll see is that 4 of these solutions are exactly the same. And so these 4 solutions all have a score, meaning the objective function's value when we're done is 235.8. So those 4 all came out with the best solution that we know of, but twice it did not do so well. One time we ran it and the objective function was only 320 instead of 235. Another time it was 310. So that's substantially worse in terms of the cost function. So in essence, for best results, going to try running k-means multiple times with different random starts. So one other thing I want to say about the objective function that we're optimizing, it's a bit of a weird objective function because it has these artificial numbers in it, the cluster means, the mu i's. And so you might ask, is that really a function that makes sense to optimize? Why are we optimizing that function? And I think the one thing that sheds a little bit of light on that is that we can write another objective function that always has the same optimum, but does not involve these cluster means at all. This is an objective function that's purely specified in terms of the input points and the cluster assignments. It's called the within cluster variation. And so here the objective is to find an assignment of points to clusters, a label vector y, that minimizes this following formula. So we're summing over all of the clusters. Within each cluster, we're going to look at every pair of points, with index j and index m in cluster I, and we're going to take just the square of the distance between those 2 points. So one more time, we're summing over all the clusters. Within each cluster, we're taking the sum of distances between all pairs of points and dividing by the size of the cluster. The minimizer, when you have the y that minimizes this function, the objective function is equal to twice the original objective function that I showed you. It is a worthwhile exercise to show that, but it's actually pretty hard. It's harder than it looks. But again, the nice thing about this expression is that there's no mu i's in there. This is an expression that depends solely on input points and the assignments and nothing else. So this objective function does not suggest the k-means algorithm. The other objective function is better at motivating where k-means comes from and why it works. Yeah? If you have a lot of variation in results that you get, then is that k is too large? That's the question. I don't really think so. I think that this example I showed you here is kind of a counterexample to that. And when you look at this, it's obvious that 4 is the right number of clusters. That's just what our eyes tell us instantly when we look at it. So changing k is not going to really fix this. If you run this multiple times with different starts, sometimes you will get the natural clustering that we would expect. But sometimes, like in this case, we don't. When you run a clustering algorithm like k-means clustering, one thing you need to think about is, do you normalize the data before you run the clustering algorithm? And for that, my answer is exactly the same as the answer for when you run PCA, do you normalize the data? So everything I said on Monday about when to normalize the data and when not to, that applies here as well. So, yeah. Mm-hmm. Sorry, say that a little louder, please.
You're not for sure about what value it should be.
Yeah.
You try a few and see which one you like.
When you're not sure what k should be, yeah, that's one thing you can do, is you can try different values of k and see what's better. It's a little tricky to compare, though, because, I mean, as k goes up, the objective function is going to go down. That's to be expected. So maybe what you're looking for is a sudden step where a lot, and that's a good sign. But there's also a whole Wikipedia page on the topic of deciding what k should be. So check that out if you want to know more. Other questions about basic k-means before I go on to modified version of k-means? It's also worth knowing about a variant of k-means called k-medoids. It's pretty similar to k-means, but it generalizes the idea of k-means clustering for situations where you're not using the Euclidean distance, but rather you want some other similarity metric between different points. And the reason for this is if you're not using the Euclidean distance as your metric for point similarity, then means do not make sense. Means are the right thing to do in the Euclidean metric only. So here, to get the ball rolling, first of all, we need to decide what metric we are going to use. So I'm going to assume that there is some distance function, d of x and y, that dictates what is the official distance between 2 points, x and y. This distance function is also sometimes called the dissimilarity between the points. Now, this can be pretty arbitrary. Ideally, it's likely to work better if you pick a distance function that satisfies the triangle inequality, but you don't have to if you pick a really wacky not metric that doesn't satisfy the triangle inequality, then it still might work as long as d is somewhat sane. This is the triangle inequality if you're not familiar with it. Now, sometimes people use the L1 norm. Sometimes people use the L infinity norm, which do satisfy the triangle inequality. But sometimes people just specify a matrix of pairwise distances between all the sample points. And sometimes that works well, too. So an example of this is, suppose you have a database that tells you how many of each product your customers have bought. You'd like to cluster together customers who buy similar products. But if you use the Euclidean distance to cluster your customers, what you're likely to get is one big cluster with all the customers who have only bought one item from you. That's not really right. Even if someone's only bought one item and therefore they're very close to the origin, you still want to treat them completely different from someone who bought a totally different item. So it makes sense maybe to cluster by the angle between two different customers in your database rather than the distance between two customers. And so you can do that. That'll be a good dissimilarity metric, but it's not Euclidean. And means don't make sense in that context. So we replace the mean with something else. And what's usually used is something called a medoid. And what's interesting about the medoid is that it is always a sample point. It's one of your input points in your data set. So it's not, when we were computing the mean, that was an arbitrary point in space that was usually not a sample point. But now we're always going to be using a sample point as our cluster center, so to speak. And it'll be the sample point that minimizes the total distance from that sample point to all the other sample points in the same cluster. So again, the medoid of a cluster is always one of the sample points in the cluster. Other than that, you just run k-means in the same way, using whatever your distance function is. So k-means itself doesn't really change, except that we have a different way of computing cluster centers. Any questions about that? Yeah. Well, in the original objective for k-means, you're squaring those distances. Here, when you choose a cluster center, we actually don't square the distances. So that's a subtle but important difference. Yeah, so what you said plus the difference I just said is what happened. So now I want to move on to an entirely different clustering method called hierarchical clustering. Now, hierarchical clustering essentially creates a tree. And within that tree, you can think of every subtree as being a cluster. So, in other words, you should think of some of the clusters as being made up of smaller clusters, and those clusters are made up of even smaller clusters. And there's essentially two common methods of building these hierarchies. One is called the bottom-up method, also known as agglomerative clustering. And here the idea is that we start by saying each point is in a separate cluster of its own. And then we're going to take those n clusters and we're going to start fusing them together. So we're going to repeat a step where we pick two clusters and fuse them together. By contrast, there's a second method that's called the top-down method. Which is also sometimes known as divisive clustering. Here what we're going to do is we're going to start with all the points being in one big cluster. And then we're going to split that cluster into two clusters. And then we're going to split each of those two clusters into two smaller clusters each. So to sort of illustrate this with a diagram, here's 6 points. How could I cluster those with agglomerative clustering? Well, like I said, initially I'm going to call each of these a cluster. So my red loops here, those are clusters. And then I'm going to say, well, let's pick two of those and put them together into a single cluster. These two are closest together, so I'm going to pick them. And then two more clusters that are closest together, group them into one cluster. Repeat, group these two into one cluster. And then maybe now which clusters are closest? Well, these two clusters, I can group them into one cluster. And then the final step is I group the two surviving clusters into one. That's agglomerative clustering. divisive clustering, let's take the same point set, essentially. And, well, I didn't get the distances right, but who cares? The idea here is, initially we're going to view that all as being part of one big cluster. And then we're going to pick a way to subdivide it into two smaller clusters. And the bottom cluster, we'll subdivide that one again. The top cluster, we'll subdivide that again. And keep going until every input point is in its own cluster. Now, when the input is a point set, as I've illustrated here, usually agglomerative clustering is used a lot more in practice than divisive clustering. But when the input is a graph, it's the other way around. The common way to do graph partitioning into smaller graphs, it's divisive. So let's look at a way to do bottom-up agglomerative clustering. My suggestion was, if two clusters are close to each other, let's group them together first. So let's quantify that. We want a distance function that we can use to say, okay, here are two clusters. How far apart are those clusters from each other? So you give me two clusters, A and B. Each of those clusters might already contain quite a few points. So it's not obvious what the distance between them should be. There are a number of different distance functions that are used for pairs of clusters, and I'll tell you about 4 of them. The first one is called complete linkage, and that one says that given two clusters, A and B, we're going to look at the maximum distance between a point in A and a point in B. So literally the point in A and the point in B that are furthest apart from each other, all A-B pairs. So some of you might think, well, wouldn't the min make more sense than the max? Well, maybe. In that case, we call it sorry, I misspelled that completely. Single linkage, pardon me. So again, we've got two clusters, A and B, and now we look for the point in A and the point in B that are closest to each other. A third method is called the average linkage, and it splits the difference in the following way. What we're going to do is we're going to look at every pair that couples one point in A with one point in B, and we're going to take the average of all those distances. So to compute that, we need 1 over the number of points in A, the number of points in B, times the sum over all points in A of the sum over all points in B of the distance between those 2 points. Lastly, we have the centroid linkage. And here the idea is, let's actually take the mean of all the points in cluster A and the mean of all the points in cluster B, call them mu A and mu B, and just look at the distance between those two cluster centers. Now, just like with k-means, it only really makes sense to use the mean if you think your points are in an Euclidean space. If you think of your points as being with some other distance metric, don't use the centroid linkage. So the first 3 of these linkages can be used for any metric, any distance function, even if the input is just a matrix of distances between pairs of points. But the 4th one, no, that's for Euclidean spaces. There is a variation of the centroid linkage that uses medoids instead of the means. So that might be worth exploring in some cases. But at any rate, let's move on to the most well-known agglomerative clustering algorithm is called the greedy agglomerative algorithm. And if you know anything about greedy algorithms, this one will be pretty obvious. You just keep repeatedly fusing the two clusters that minimize the distance between the first cluster and the second cluster. And you just keep repeating this fusing of two clusters over and over again until you only have one cluster left. And if you do this in the obvious way, you have kind of a slow algorithm. It runs in cubic time. Having said that, for the complete and single linkages, there are more sophisticated algorithms that can optimize this. They're called C-link and S-link, or maybe they're called clink and slink, I'm not sure. But they run in n² time. It is possible to speed those two up. Now, once you're done fusing clusters together, what's interesting is that what you get isn't just clusters, you get a sort of hierarchy, which is often referred to as a dendrogram. A dendrogram is an illustration of the cluster hierarchy in the form of a tree that allows you to decide where to cut it, so you can decide how many clusters you're going to get. Now, one thing that's special about the dendrogram is that we use the vertical axis to encode all the linkage distances. So it gives us an idea of how close each cluster, how close the clusters are to each other within each cluster. This will be more clear when you see the picture. So there we go. This is a dendrogram. Let's look at the version on the left first. So the green bars at the bottom, think of those as being the different sample points. The x-axis actually does not have a meaning. There's no numerical meaning, but the y-axis tells you the linkage at various spots. So for instance, the very last pair of clusters that were fused together, those had a linkage cost of about 10.5. That's the distance between this cluster and this cluster. And then as you go down, you get tighter and tighter linkages, smaller and smaller linkage distances. So once you've got this dendrogram, what you can do is you can say, how many clusters do I want? Well, if I want 2 clusters, then what I should do is I should cut it here, and now I've got cluster number 1 is there and cluster number 2 is there. Okay, but what if I want 3 clusters? Okay, then what we do is we cut it here at this distance, and that gives me cluster number 1, cluster number 2, cluster number 3. Basically, by choosing a height to cut at, I get the number of clusters that I want. Or you could use the intercluster distance, like the y-axis, as your threshold for cutting. Instead of saying, I want exactly k clusters, you could say, well, I think maybe 4 is just a good place to cut. So one more time, the horizontal axis of the dendrogram has no meaning. I could swap any pair of clusters and it's the same dendrogram. Only the vertical axis has a numerical meaning. So now that we've seen what a dendrogram is and what it looks like, let's look at 3 different linkages and what kinds of dendrograms they give us for the same data set. So here's the same data set 3 times. If we use the single linkage on the right, this gives us a very badly balanced tree. It's very lopsided and deep because we are always using the 2 closest clusters. Remember, the single linkage says the closest pair of points in cluster A and cluster B. That's how you decide who to link together. That tends to give you very unbalanced trees. The complete linkage, by contrast, tends to give you very nicely balanced trees because now we're looking at the maximum distance between 2 points in the cluster. And so as clusters get bigger, it's harder for them to fuse with other clusters. So that's why you get a very nicely balanced tree. The average link, decent balance, not quite as balanced as the complete linkage. The single linkage doesn't look very good. It's sensitive to outliers. The root of the tree, the left child has just 1 point. Like literally the very last linkage was a cluster with 1 point, and a cluster with all the other points got linked together at the very end of the algorithm. And so this outlier point has undue influence. Is that really what you want from your clustering algorithm? Really? There might be cases where you do. So in most applications, you should probably choose the average or complete linkage. One other thing you might want to be aware of is that the centroid linkage, which I'm not showing you here, can cause inversions where you don't get this nice looking structure because sometimes a parent cluster is fused at a